Hello students. So up until last class we looked into differentiation under the integral sign, where we learnt about if you have an integral of this type, let's say I equals to integral from a to b fxy dx dy, then in that case how we can differentiate this integral. So here so we don't need to have dy. So first let us so if we integrate this integral, then in that case we will obtain a function of y. So basically this integral is nothing but a function of y, and after the integration we can talk about the differentiability of this function I y. And if we want to differentiate this integral, let's say if we are doing di dy, then in that case we can write it as the integral a to b fxy dx, and after we perform the differentiation, we will basically bring the differentiation inside the integral, and it can be written in this fashion. Now bringing this integral, bringing this differentiation inside the integral is not that straightforward. I mean, in order to do that, we need to have some special properties for this function f. And we saw in the previous class that this function fxy needs to be continuous on a rectangular domain R, and also the partial derivative of this function f needs to be continuous with respect to y. So based on that, we also solved an example. We will continue with the similar topic, which is differentiation under the integral sign, and we will now state an important theorem in that respect. So the theorem is called as Leibniz rule of differentiation under differentiation. Leibniz rule of differentiation under the integral sign. So integral sign. Leibniz was a German mathematician. Now the statement goes like this. So this can be basically viewed as a theorem. We can consider it as theorem 2. So let fxy and fxy be continuous on the rectangle R, which is defined as all those xy such that a less or equal to x less or equal to b, and c less or equal to y less or equal to d, and let phi and psi be two functions mapping from a b to c d, be both differentiable in a comma b, then the integral, let's say gx equals to integral from phi x to psi x fxy dy is derivable or differentiable, or we can also write differentiable in on the interval a b, and our derivative can be given as g dash x equals to d dx of integral from phi x to psi x fxy dy is equals to f x y, instead of y I can write psi x times psi dash x. So, differentiation of psi x with respect to x minus f x, instead of y I can write phi x times phi dash x, and plus integral from phi x to psi x f x y dy. So, first of all, if we look at this integral, obviously if we integrate with respect to y, and if the limits are both functions of x, then in that case after substitution we will basically obtain a function of x, and then we can talk about its differentiability. So, to talk about its differentiability makes sense because we ultimately obtain a function of x only. Now, in order to do the differentiation on this interval a to b, this function f needs to have these two important properties, that it needs to be continuous, and also its partial derivative with respect to x also needs to be continuous. And then in that case we can talk about its differentiability, and the rule of differentiation is we first substitute f x psi in the place of y, we substitute the upper limit, which is f of x psi x times psi dash x minus f x phi x times phi dash x, plus the derivative will come inside. Now, here whether we would like to see whether this Leibniz rule of differentiation under the integral sign is actually valid when the limits are constant or not. So, if I substitute phi equals to a and psi equals to b, then b is constant, so psi dash x will be 0, and phi is constant, and in place of phi we have a. So, phi is constant, and therefore phi dash x equals to 0 as well. So, the first two term will vanish, and then in that case we are left with the integral from a to b f x x y dy. So, which is basically our theorem 1 for differentiation under the integral sign. Remember, theorem 1 was something which dealt with constant limits. So, that means both the limits, lower and upper limits, were constant in case of theorem 1, and in case of theorem 2 you have both the limits as a function of x. So, this is a general rule of differentiation under the integral sign, or sometimes it is also called as Leibniz rule of differentiation. So, for the proof we are not concerned with that, because the proof is relatively long and it's out of the scope of this syllabus. It's just that knowing this statement is very important, because we require this statement quite often in our work, and when we also solve some exercises and some problems, we definitely require this formula to solve those problems. So, now we are ready with solving the examples. So, in order to do so, let's start with our first problem. So, to start with our first problem, let us consider example 1. So, find the differentiation of the following integral with respect to x on 0 to 1 times 2 to 3. So, that is, our rectangle R is all those x and y such that 0 less or equal to x less or equal to 1 and 2 less or equal to y less or equal to 3. So, we need to find the differentiation of the integral given as I x equals to integral from x square to x to the power 4 x square plus y square dx. All right. So here our function f. So here our function f is, so let's go to the solution. So of course here we will apply the Leibniz rule of differentiation. So first of all we see that both the functions let us start this interval by 0 as well, so that we have a bigger interval. So 0 to 1 and 0 to 3. So of course these two functions are continuous, both the upper limits and lower limits in this interval. They also map from 0 1 to 0 3, and this function, this x square plus y square, since it is an algebraic function, in a way it will be continuous, and not only that, partial derivative with respect to x is also continuous in this domain. So all those conditions for the Leibniz rule of differentiation is satisfied, so we don't have to worry. Now, or we can write at least one line. That Leibniz, the conditions for Leibniz rule of differentiation is satisfied. So we have di dx equals to ddx of integral from x square to x to the power 4 x square plus y square dx, and then this will be x square plus y square. Then instead of y we substitute the upper limit. So let us substitute the upper limit here, which is x to the power 4, and then its square is basically x to the power 4 whole square times the differentiation of the upper limit, which is basically ddx of x to the power 4 minus x square plus y square, and instead of y we substitute the lower limit, so x square whole square times ddx of x square plus integral from x square to x to the power 4, derivative of this one with respect to x, so it is basically ddx of del x of x square plus y square dx, and then this can be written as x square plus x to the power 8 times differentiation of x to the power 4 would be 4x cube minus x square plus x to the power 4 x square plus x to the power 4 times 2x plus integral from x square to x to the power 4 x square to x to the power 4. The derivative of the second term will be 0 and the first term is 2x, so I can write 2x dx. So this is basically x square plus x to the power 8 4x to the power 3 minus 2x times x square plus x to the power 4, and this one will be 2 times x square by 2, so this is basically just x square and we substitute x square. So we substitute x square to x to the power 4, and then whatever is the limit we just write the limit here. So we substitute x square, so this will be x to the power 8 minus x to the power 4, and we just calculate, and that will be the differentiation of the integral. So this is how we calculate in this case the differentiation of an integral. So what we do, we just apply the Leibniz rule of differentiation. So psi x to phi x to psi x, and then we integrate with respect to y I'm sorry, so here we are integrating with respect to y, so this will be 2x dy, so this will be 2x dy, and then we can write this as 2x times y integration from x squared to x to the power 4. Sorry, the integration here the integral has to be with respect to y, then in that case we get the integral with respect to x. Yes, so if we integrate with respect to y, then we will basically obtain a y here, and this is of course 2x, and then in that case this will be 2x times y, and the limit we can substitute x to the power 4 x square, and then we calculate, which is basically a calculation of a simple algebraic expression. So this is how we calculate the differentiation of an integral, and next we work out few more examples just to get the concept a little bit more clear. So example 2, or I would say 3. So assuming the validity of differentiation under the integral sign, show that integral from 0 to infinity e to the power minus x square cos x cos alpha x dx equals to 1 by 2 square root of pi e to the power minus alpha square by 4, where alpha is any positive number. So we have to show that this integral e to the power minus x square cos alpha x dx is equals to this. So here it's very clear that alpha is the parameter, since we are integrating with respect to x. So we can write here I alpha equals to integral from 0 to infinity e to the power minus x square cos alpha x dx. So this is given. Now let us differentiate both sides with respect to alpha. So this will be di d alpha, and our partial derivative will go inside of the integral. So this will be 0 to infinity x e to the power minus x square, differentiation of cos x is sin x, and differentiation of alpha x is x dx. All right. So this is our del alpha di by d alpha, and now we integrate by parts both sides, then we obtain di d alpha. So we integrate by parts, and then this will reduce to 1 by 2 e to the power minus x square sin alpha x integral from 0 to infinity minus 1 by 2 alpha, this will be integral from 0 to infinity e to the power minus x square cos alpha x dx. So here we are integrating this whole thing by parts, and considering sin alpha x as the first function, and x e to the power minus x square as the second function, we will obtain this integral here. This is basically a part of method of substitution and all, so it's pretty straightforward. And from here, when x is infinity, then this whole thing will go to 0, and when x is 0, then again this whole thing will go to 0. So the first term will not play any role, and the second term can be written as I alpha, because this is our I alpha we started with. Therefore our di d alpha is basically this ordinary differential equation. So if we integrate both sides, then in that case this will be di d alpha. So di by I is equals to minus alpha by 2 d alpha. So if I integrate, then this will be log of e I, and if I integrate on the right hand side, then this will be alpha square by 2 times 2. So that means this will be 4 plus some constant c, and this can be written as I alpha equals to e to the power some c times e to the power some c plus e to the power some c. Is it plus? No, it's minus alpha square by 4 times this. All right. So now we find out the value of I0. So when alpha is 0, then this will be e to the power c minus 0. So basically e to the power c. So let us call this as equation number 1, this as equation number 2. So we have to evaluate the value of c, and I0 on the left hand side, basically I0 is, when I substitute alpha equals to 0, then this is basically cos 0, and cos 0 is 1. So we have I0 equals to integral from 0 to infinity e to the power minus x square cos 0 dx. So cos 0 is 1, so this will be integral from 0 to infinity e to the power minus x square dx. And in our previous lecture, we just we proved that this is nothing but our gamma half by half. So that means square root of pi by 2. So this relation we already proved in previous chapter, in previous topic. So combining these two, we can see that. So combining these two, we can see that we can see that c will be, so if I choose c as let us say log of c, so if I choose c as let us say log of c, then in that case this will be log of I c, so this will be e to the power minus e to the power minus alpha square by 4 times c. So this will be the c will come here, and this will be c times e to the power minus alpha square by 4. So we can, it's all about playing with the arbitrary constant. So we can play with this arbitrary constant as we please. So we can write it as c e to the power minus 0. So this is basically our c. So our c is basically I. So that means from 2 and 3. So from 2 and 3 we have, from 2 and 3 we have I0 equals to c equals to square root of pi by 2. So from here we can write, from 1 we can write I alpha equals to square root of pi times 2 e to the power minus alpha square by 4. And this is what we needed to prove. So you see, by considering this integral, so this integral here, it's also very important to notice whether this falls under the category of differentiation under the integral sign or not. So if it does falls into that category, then in that case we have to identify the parameter. It is usually the variable with respect to which we are not differentiating, not integrating. So here we are integrating with respect to x. So alpha is the parameter, and then after the integration we will obtain a function which is a function of alpha only, and therefore we can write it as I alpha. Now we differentiate this I alpha with respect to alpha, and we obtain this integral here. Then we integrate this integral by parts, and then we obtain this this here, and we can evaluate the limit, and we realize that the limit in the first term vanishes. Therefore the second term will reduce to minus alpha by 2 times I of alpha. And next we integrate, and after integrating, choosing a constant, we know that from our +2 level that we choose this constant in such a way that you can use those logarithmic formulas, and then you can write it here as e to the power that whatever you have on the right hand side. So instead of choosing c, I chose a logarithmic to the base e, and then I can bring this log here, and then this will be log of I minus log of c, so it will be log of I by c, and then on the right hand side we will obtain c times e to the power minus alpha square by 4. Now we need to evaluate the value of c, so what we do, we substitute alpha equals to 0, and therefore this will reduce to square root of pi by 2, and by substituting the value of c here, we will obtain required I alpha, and this is what we needed to prove in our example. So in this problem, this is what we needed to prove. So it's not that how to say complicated. It might get sometimes lengthy, but solving this type of problem would not be that much complicated. Next, so let me give you one or two more examples, but I would say I would assume that solving those problems can also be fairly easy, because they do not involve such a complicated calculation or something. So another example could be show that integral from 0 to a log of 1 plus a x divided by 1 plus x square equals to 1 by 2 log of 1 plus a square tan inverse a. So again, if you look at this integral, it might look a little bit complicated, but on the right hand side we have an integral, we have a value of the integral which sort of involves log and tan inverse. So I can write I equals to integral from 0 to a log of 1 plus a x divided by 1 plus x square. Now again, here we are integrating dx. So here we are integrating with respect to x. So that means a here will be considered as the parameter, and we have an a in the integrand and as well as in the limit, upper limit as well. So this I of a is not that simple to differentiate. Here we have to use the Leibniz rule of differentiation before we use the simple our function 1 theorem 1 of integral under the differentiation under the integral sign, but in this case we have to use the Leibniz rule. So the Leibniz rule can be applicable here. So di dA, which can be given as d dA integral from 0 to a log of 1 plus a x divided by 1 plus x dx, and this can be written as log of x y. So instead of y, I substitute a, so this will be 1 plus a times a divided by 1 plus x square, and this instead of a, we are substituting again a times side as x. Side as x is this one here. So this will be d dA of a minus this second one would be log of 1 plus, instead of a, I will substitute 0 times x divided by 1 plus x square, and then this will be d dA of 0 plus integral from 0 to a, we have d dA, so this will be 1 by a square x square times a 1 plus x square dx. right? And differentiation of Ax would be A times 1 by so differentiation of this function would be 1 by a plus x square plus 1 by x square. So it will be slightly different. So the value of this integral, the value of the differentiation would be x 1 plus x square 1 by 1 plus ax. So here this will be 1 by 1 plus ax time, and in the numerator we will have an x actually. Yes. So this will be the value of the differentiation of this integrand with respect to x here, and now we have to again calculate like we did before. So substitute, so this will reduce to a function with respect to a. So here this will reduce to a. Yeah, and then we basically formulate the ODE. So let me go to the next page. So we will basically obtain an ODE of following type. So the ODE will look like dIdA equals to 1 by 2 1 plus a square log of 1 plus a square plus a tan inverse a by 1 plus a square. So this is the required ordinary differential equation that we will obtain. It involves a slight simplification or calculation here, but since it is relatively big, I leave this to the students, and ultimately we will obtain an ordinary differential equation of this type, and from here we will basically obtain I0 like we did before, because we will obtain a constant, and then we substitute the value of the constant to solve this ordinary differential equation, and that will give us the value of this integral I which we started with. So based on these calculation, we see that we can be able to evaluate this type of integral, which is basically involves another parameter, and these type of integral do come up quite often in engineering sciences also, and there we might need to do the differentiation under the integral sign. And this theorem 1 and theorem 2, which is basically Leibniz rule of differentiation, will prove to be very handy, and I will include some more examples in your assignment sheet, and I look forward to your next class. Thank you.